So few words about the processing that we are applying for this production. For the global view of the processing, is more or less the same that the one that we are applying on the conventional 1Hz production, but with few K differences. The first one is that we are using in upstream of this production the 20 Hz posting rate level 2 product. And we try to keep this 20 Hz resolution as long as possible during the processing and apply a subsampling to have a 5 Hz product as a final step of the processing. As we are working with 20 Hz product, we have a lot of noise in this product compared to the 1 Hz. So we need to use up-to-date standards and corrections that help us to reduce the errors on the product and better resolve the small scale signal that is of interest for us. So when we consider the operational production for the Copernicus Marine Service, we apply what we call the high frequency adjustment corrections. It is an empirical correction that reduces the noise on the sea level using the correlation between the sea level 8 noise and the significant wave rate noise. And where we are working for R&D, we can also test different I'd say experimental processing that are still on R&D and that also contribute to reduce the error at short wavelengths. We also try to use up-to-date K parameters, like for example, mid-sea surface field. So we try to use the up-to-date fields, and when we can, we also compute what we call the mean profile, which is an estimation of the mid-sea surface directly along the tracks of the different altimeters. We apply also different quality control criteria in order to reject what we consider as invalid measurement. And here, as we are working with the 20 Hz upstream product, we adapted the different criteria that you apply specifically for this posting rate. And then we apply low-pass filtering on the sea level anomaly with the aim to remove all the short wavelengths where the error, the noise dominate over the signal of interest. So here, for this 5 Hz production, we have the strategy to adapt the cutoff wavelength differently for each altimeter considered, and we adapt this cutoff to the observing capabilities of the different altimeters. When we also try to estimate geostrophic currents in the across-track direction, using in upstream the filtered sea level anomaly produced by the previous step. And as I said before, the final step is to subsample to the sea level in order to deliver a 5 Hz product to the users. Why 5 Hz and not 20 Hz? Because we consider that it's a good compromise between the observing capability of this product and the user needs. So this is an example of validation of this product. So you can see here result obtained for the near real-time production for the Copernicus Marine Service. On the left, you have an example of the sea level anomaly along some tracks of different altimeters in the Alboran Sea over a 10-day period. On the top, it's for the conventional 1 Hz production, and on the bottom for the 5 Hz product. So you see that there is a good agreement between the two products, and we also see that the 5 Hz product can go closer to the cost compared to the 1 Hz. And if you look at statistic along the track of the different altimeters, we also find that we have a better variability rate of the 5 Hz products, so with the cost compared to the 1 Hz. So on the right, you have an example of the variability rate obtained along the Sentinel-3A tracks in orange for the 5 Hz product and in blue for the 1 Hz product. And if we look at the evolution of the sea level anomaly variance when approaching the coast, we can see that the 5 Hz product presents a lower variance than the 1 Hz product far from the coast. So this proves that the processing applied efficiently reduces the noise on the 20 Hz measurements that we are using in upstream. And when we are go closer to the cost, we can see that the variance of this product is increased more higher than the one observed for the 1S product. But with this kind of diagnostic, it's difficult to say that it is a degradation of an improvement. Also because near the cost, we are comparing product with a different viability rate, so it's not very comparable. So to go deeper in the validation of this product near the cost, we also try to compare the 5 Hz long track product with independent tag gauge measurements. We did that for the European cost with the sample V2 version delivered with NES. So this version of the product also go closer to the cost compared to the 1S version. And on the map here, you can see the reduction of variance of the difference between the altimeter product and the tag gauges when we are using the 5 Hz product instead of the 1S product. So blue color means that the 5 Hz is better in agreement with the tag gauge compared to the 1 Hz. So at the global mean over the European region, we have a good reduction of the variance of the difference with tag gauge when we are using the level 3 5 Hz product. This reduction reached nearly 5% to 17%, depending on the altimeter considered. And as we go closer to the cost with this product, we also observe that we have a higher number of data pair altimetry tag gauge to compare when we are considering the 5 Hz product instead of the 1 Hz. We can see on the map that there are still some red color, means degradation of the consistency with tag gauge when we are considering the 5 Hz product. So this means that we still have some progress to do on this processing. Another thing that we can look at for the validation of the 5 Hz product is to analyze the spectral content of the sea level anomaly. So here we stay with the 20 Hz posting rate of the product, so just before the subsampling step, in order to have a global anterior view of the spectral content of the product. The image here are in black line. You can see the observed spectral content of the sea level anomaly over a small box in the Northeast Atlantic area for 2 seasons, winter and summer. And the red dotted line represents the fit of the different of the content of the spectrum for different wavelength range. So you can see the fit of the noise plateau here. And we can also fit the slope corresponding to the mesoscale or balanced motion at a long wavelength. And we also try to fit a slope at smaller wavelengths that should be characteristic of the unbalanced motion as presented by NIFU also with the spectrum for the SWOT mission. And what is interesting here is that first we can fit a slope on these small wavelengths. This is something very difficult when we consider the 1 Hz product, especially if we have only a short temporal period with this product. And we also observe that there is an important seasonal variability of these different parameters. And this variability is consistent with the one reported by other authors with models, like, for example, Q and R in 2018. So this is very encouraging. However, we know that surely part of the signal at short wavelength is still impacted by residual errors on the measurement. So we need to go deeper in this analysis and better extract what is the true signal and what is the errors. We also need to extend this kind of analysis over the global ocean to confirm also that we have signal of interest in these small wavelengths. So this is a work ongoing. Now some example of application with this level 3 5 Hz product. The first application is that we can use this product for assimilation in numerical models. So this was tested by Mercator Ocean with a regional model over the Iberian region. And they also said that when they simulate the 5 Hz product instead of the 1 Hz, they have a significant gain, reduction of the error of the model by about 10% for the C-level C-surface 8. They also observed a positive impact for other variables from output of the model, like, for example, sea surface temperature at the surface and in the bottom, which is better consistent with other observation when assimilating the 5 Hz product. And they also observed a reduction of the error for the surface current. So this is illustrated on the map in the bottom here. You can see the variance of the difference between the surface current in output of the model and with independent high frequency radar measurement in the Bay of Biscay. And you can see that when the model assimilates the 5 Hz product instead of the 1 Hz, we have a net reduction of the variance of the difference with the high frequency radar measurement. Another example of application is that we can use this 5 Hz product in upstream of mapping process. So we tested that with over the Black Sea region. And you have an example of the result obtained. So this map shows in background a sea surface temperature fields that underline the presence of an eddy near the coast here. And the black curve shows a contour of absolute dynamic topography deduced by the maps constructed with altimeter product. So the first map shows the result obtained when we are using the 5 Hz level 3 product in upstream of the mapping, and the other map is what we obtain when we are using the 1 Hz conventional product. So you clearly see that when we are using the 5 Hz product, we better resolve the eddies near the coast with a very clear closed contour of absolute dynamic topography. It is not the case when we are using the 1 Hz conventional product. So we also use in this mapping an optimized mapping process. It is optimal interpolation, but we force the correlation scale to follow the gradient of bathymetry along the track. So this reinforces the intensity of the current that we obtain along the slope of the bathymetry. So to conclude, you know now that there is some along track sea level product available with a 5 Hz processing rate. So operational production is available on the Copernicus Marine Service since November last year, and that covers the European Sea. And we are preparing the production for the global ocean, to be available in November this year. So this is a product first dedicated to the regional application, but the quality seems quite good near the coast, at least when we consider the distance larger than 5 kilometers to the coast. So do not hesitate to test them and give your feedback. It's always valuable to improve the product in the future. And we still continue R&D with CNES. So we are preparing a sample of product for the global ocean that should be delivered before the summer this year on Aviso. And we also try to make a link between different projects that focus on the coastal area. For example, the coastal dedicated product presented by Florence Birol on Tuesday, or Clear Tempo project presented by Francisco Necho. We also try to preparing the processing of the SWOT measurements. So first, the nadir measurements that we will try to include in our processing as soon as possible. And we are also working on the definition of the processing that we will need to apply on the carrying measurement for future production also. In the same time, we are working on new mapping methodologies, like multiscale, multivariate, or multicaptor, or artificial intelligence mapping. So this is not specifically for the coastal area, but we will try to do our best for the coastal maps. And all this R&D activity are preparing the future evolution of the operational production in the Copernicus Marine Service. I finished with some recommendations. So many of the recommendations I have been already done discussed during the past day. But I think for the space agency that it's important to continue the effort to improve the processing of the altimeter measurement and reduce the noise and improve the observability of the small wavelengths in coastal area, but also offshore. So continue to work on different retracking, geophysical and environmental correction, also different observing techniques, and deliver us good altimeter products. As I said before, it's important to ensure the continuity of the sea level and other variable between the coast and the offshore area. And it's also important to take care in producing the 20 Hz level 2 product in order to have an optimal 20 Hz product. This kind of product is more and more used, especially for the coastal application. So we need a true 20 Hz product with geophysical and environmental correction available at 20 Hz and not only 1 Hz, especially for some K parameters. We would like also to have additional correction, like high frequency adjustment correction that contribute to reduce the noise at short wavelengths. So please try to include this correction in the different two products. And it's also important to ensure minimal calval activity on the 20 Hz product. No large part of the calval activity is done at 1 Hz, but it's important to have a minimal one activity for the 20 Hz. And recommendation for users. So I said before, test the product, give your feedback, and express your needs for the future production. Thank you.
Are there any questions to Isabel? I might ask a question then. So the differences between the 5 and 1 Hertz data you see in the validation with tight gauges, do you think that's significant, and how do you interpret these differences? So is it really the improvement in resolution that you're better, or are there any other causes of this?
Yes, we think that it's a true improvement because we know that we can resolve shorter wavelengths than the 1 Hz product. We can go closer to the coast, so this is interesting for this community. So this was quantified, and it's a true improvement, yes.
Okay. Okay, then the next speaker is Thomas Fernandez.
Okay, welcome everybody. I'm Tomás Fernández from the University of Cádiz, and I will present the work where we try to establish a relationship between the mean sea level and the stream coastal flow event along the European coastline. So all of us know that the vast quantity of energy accumulated in the ocean can treat the assets located in the littoral areas, where basically we have the release of this quantity of energy in several ways, like breaking waves, erosion, coastal flooding, etc. Okay, if we add to this situation very intensive populated areas like the coastline in Europe, where approximately 2 million of people lives very close to the coastal. This is the actual situation, but this number is expected to be increasing in the next year. So we have a very explosive cocktail where we have a situation where the many impact can happen. And this is specific dramatic in the context of climate change that we are living actually. So the past event can help us to understand this, this event, the relationship, the specific contribution of each component to the stream water levels, and know this specific contribution and the relation between them can help us to improve the preparedness and the mitigation in this event. So there is a lot of literature about the contribution of the waves, the resonance in the semi-enclosed basin, the contribution of the wave age, the interaction between the waves and the surge, etc. And also the tide and the surge have been studied in the specific areas like the North Sea, where there are intensive non-linear interaction between them. It can cause the delay of the peak of the storm, the increase of the peak of the storm in some areas, or the decrease of the peak of the storm in other areas. So, but what about the mean sea level contribution? Okay, we know that this can be understood, and this has been studied from altimetry data sets, very intensive, but not maybe from the point of view of the stream event, of the hazard, coastal hazard, okay? The reason why is because apparently it is it's contribute with a very few centimeters in relation with other contributions like a storm surge or tide in some areas. But if you look to the stream value analysis of several tidal gauge across Europe, you can see that the difference between 50 or 100 year return period water level is really a few centimeters. So a few centimeters can make the difference between the coastal flood event that counts impact or not. So even if the mean sea level is a low contribution compared with other, should be understand which is the possibility that this contribution can increase the potential impact of a coastal stream event like caused by waves or by the storm surge. So in that way, we identify this lag and we try to analyze this, which is the contribution of this mean sea levels, which is the contribution of the high signal of surge and tide in the stream water levels, and which will be the relation between this contribution and the coastal flood detected, the historical coastal flood detected in Europe in the last decades, okay? So we use altimetry because it have some limitation, like the poison rate, etc., but we have a coverage, full coverage of Europe and coastline of Europe. So basically, we use two data sets. One is the sea level level 3 that we download from Copernicus. This is already a deprecated version or data set. The important thing is that we use the SL corrected. And to compare or to try to establish some relationship with the coastal flood event, we create a specific storm impact database combining different databases, Hanse, Risky, or the British one. But we call it a total number of 500 events. We coverage from 93 to 2016. And we try to normalize the geolocalization of this impact to the NUTS level 3, which is the statistical region in Europe. So basically, we try to split to understand which is the specific contribution of monthly mean sea level, storm surge, and tide. Okay, we reconstruct the storm surge, adding the dynamic atmospheric correction to the sea level anomaly and subtracting the monthly mean sea level. Then we define the stream water level, like the water level that are larger than 95 percentile. We create a grid with tiles. We divide the area in Europe in 1 degree by 1 degree, and we create time series with all the measurements footprint that are inside of this tile. Okay. Then we define the monthly mean sea level anomaly like the average, the subtracting the average. So the climatology with this specific mean in the month. And well, we get the annual cycle and the variability. I will not spend time on that because you know better than me probably, for sure. So, but basically the idea that I want to remark is that you see the larger variability in the month of January, February, and March, matching with the peaks of the storm surge level, so the water level, the stream water level derived by or driving by wind and pressure, okay, in many areas. So in these areas match the areas where this component are more important. So here, for instance, we have the contribution, relative contribution of the monthly mean sea level respect to the storm surge level. We have relative low contribution. And here in this ternary diagram, we have the contribution of each component. The vertex is 100% and the opposite side is 0%. So basically we look in the North Sea, for instance, clearly the tide is quite important, but the mean sea level is still 10–20% of the signal can arrive in some extreme events, okay? So this is one I want to remark. If we look to the mean sea level, to the monthly mean sea level in the Baltic Sea, so in this area, we look to the stream, it can arrive to 30–40%, okay, the contribution of the mean sea level in these areas. Well, when we look, this is the plot that we create overlapping the areas, the impact, the different impact with the climatology of the monthly mean sea level, okay, you can see that there is a lag between the average, I mean the annual cycle, of course, there is a lag between the maximum, the peaks in, say, October or September, with the peaks of the storm surge, so the wind and pressure driving maxima on the water level, there is a lag. And so there is no correlation, basically, between the stream event, so the coastal flood stream event recorded in Europe, and the mean or the annual climatology. Okay, this is not surprising, this is what we expect. But if we go a bit deeper and we start to look in the fraction of each component and the variance, the monthly variance of this component, we can identify several areas where there is a relationship. Like in the central Mediterranean, there is a positive correlation. In the North Sea, there is also a positive correlation, significant correlation, and also in the Baltic Sea, showing that this specific event, not the average, not the annual, but this specific event have been influenced by the monthly mean sea level, okay, specifically in the extreme. Go still deeper, if we look into the anomaly, so the difference between the current monthly mean sea level and the average monthly mean sea level, we see that there is a positive correlation between these anomalies, so the anomaly of the extreme events that have caused impact along Europe are most positive than negative. And this positive correlation is significant in the central Mediterranean, in the North Atlantic, in the North Sea, and in the Baltic Sea. So giving us the idea that these few centimeters are important. I mean, there is a specific relationship. Usually this mean sea level is not considered dynamically in the climate projection or even in the analysis, usually with numerical models, with 2D barotropic models. So giving us the idea that this is important to be considered. Just to conclude, the main conclusion of the work is that we find that there is no mean or there is no relation between coastal flood event around Europe with the average, with the climate, with the annual cycle, but there is with the fraction of component, and there is larger and in more specific region, a consistent or a correlation, positive correlation between the mean sea level anomalies and the stream events, okay, that have caused impact. These regions are those that have a largest interannual variability, as we show at the beginning, indicating that the role of this monthly mean sea level should be considered, in future work to analyze the projection for the climate change or to understand the past event in the last decade. The altimetry data can help. We have the idea now to do this work using coastal altimetry to improve the result and including also the waves component. And that's all. If you have any question, I will be happy to answer.
So we have time for different questions. No questions? Okay, thank you, Thomas.
Thank you.
So next speaker is Hughes Horsman.
Hi everyone, I'm going to talk about vertical land motion, which might not be of immediate interest to some of you working with coastal altimetry data, but it is of course very important if we think of long-term relative sea level changes, and it's also important to know vertical land motion at tide gauges when we want to validate coastal altimetry data. And so this presentation is not so much focused on coastal altimetry, but rather on the effects and the variations of vertical land motion and some challenges we're currently facing in estimating that. First of all, I'd like to give a very general introduction into the major driver of vertical land motion, because it is widely known that can be highly regionally variable. Here I show some relative sea level change observations over the last approximately 80 years in the upper plot. So again, these time series are shifted against each other, and that scale is in meter. And below I show the global mean sea level change over the same period, like 80 years. The scale is a bit wider than the upper scale because that signal is quite small compared to these relative sea level change variations estimated at tide gauges. As can be seen, these stations are show some highly nonlinear variability, and that's mainly caused by the effect of vertical land motion rather than the one from absolute sea level changes. And one process contributing to such nonlinear variations are tectonic activities, and that can also lead to instantaneous displacements, even can be in the order of almost a meter. So it's really a significant impact. Also, we know that many major cities have been subsiding due to human effects, like groundwater pumping, and we see this in Manila and Bangkok, tide gauge time series, where you see really an acceleration from the 60s on, and that's really caused by human-induced groundwater pumping and subsidence. And also the signal is pretty large, almost 80 centimeter change. And finally, we have these large-scale processes like GIA and other natural processes and mass loading changes. So as these variations can be very large compared to the absolute sea level changes, we need to understand this. Not only, for example, if you think of sea level reconstruction, but also for the contemporary era when we want to validate coastal altimetry, for example, and trends. And of course, we kind of want to understand what's going to happen in the future, so we want to find ways to project vertical motion. However, when we want to estimate vertical motion, ideally everywhere along the global coastlines, we have a problem that we don't have observations everywhere. So the GNSS network is very inhomogeneous. So I show here vertical motion, like linear trends from GNSS data. And some regions really don't have any stations, like Africa and parts of Southeast Asia. So poorly covered. So that's one challenge, and another challenge are these nonlinear events like earthquakes, and this can really affect regions at a like continental scale. And here show the impact of the Tohoku earthquake on height changes in Japan as measured by this network. Also, you see before 2010. These points are plotted gray, so that means there were no observations at this time. So this is also a challenge. We don't have observation, so we don't have a very long time series in many cases. And in our work, we aimed at overcoming all of these problems and improving the status quo that vertical motion is usually modeled as a linear process. So we also wanted to model these nonlinear changes. And for this, we computed a vertical motion reconstruction based on a large network of GNSS stations, like more than 10,000 stations, and also based on indirect vertical motion estimates derived from differences between altimetry and tide gauge observations. And this reconstruction is computed over the last 25 years. In this slide, I quickly summarize how we generated this estimate. So here I fit the observations of heights called U to a model consisting of a linear trend component and then a set of components aimed at describing these nonlinear variations. So here this component called PC is like a time series, which is then multiplied with a spatial field, somewhat similar to an EOF approach. But for this analysis, I use a Bayesian approach to solve for these fields, because we cannot apply a standard EOF approach due to the incompleteness of the data. And these parameters are estimated point-wise, first of all, at all of these different available stations. And here I illustrate the linear trend in Japan, and then also the first component, which he captures really nicely this impact of the earthquake and the post-seismic deformation following afterwards. And after that, after estimating these parameters everywhere, we then simply interpolated the parameters in space to have a continuous estimate along the coastline, and also computed uncertainty propagation. And I think the main strength of this approach is that due to the nature of this Bayesian approach, we have full uncertainty quantified. Now, the resulting linear trends on a global map are shown here and show well-known features which have been studied before, like large-scale GIA response or subsidence Gulf of Mexico. But I think what's more interesting is how we can resolve these nonlinear variations, and that's shown here in these different time series, where I show the reconstruction in red with the uncertainties. So really we have uncertainties at every time and at every location. And also these uncertainties get larger the further we go back in time, and that's also meaningful because we have not a lot of data in the first period of observations.
And yeah, again, you see some effects like subsidence in Venice or this nonlinear effect in Tokyo. And so also some smaller variations due to mass loading changes, which also correlates here with a contemporary mass redistribution effect on vertical land motion that was based on Gray's estimates. You also see here indicated the linear trend, which is and disentangling these components like the linear long-term rate from these contemporary variations is important. For example, if you want to reconstruct sea level into the last century, and this is illustrated here. So in green, I show a relative sea level change of time series from a tide gauge. In blue, that's our reconstruction. So over the last 25 years, we have an estimate. So here, I plot a solid line, and then I use this linear trend estimate to kind of extrapolate this motion into the past. You see the uncertainties are really large, but it's mainly due to the variability at that station. And in red, we see the difference of relative sea level change and the vertical land motion, which is the absolute sea level change. And we compared this to other independent estimate of the absolute sea level change over the last century from Sönke-Dangendorf. And here we see that these two orange lines fit relatively well, and also that fits relatively well to the altimetry time series. So overall, we believe that this is important, for example, to constrain sea level reconstructions. But of course, I think there are a lot of discussions how you do it. So if you estimate the vertical land motion indirectly in sea level reconstructions, or if you constrain it, and it's still an unresolved problem. But depending on what vertical land motion estimate you're applying the tide gauges, you will end up with very different estimates, even in the global average of past sea level. So that's different absolute sea level change estimates over the last century, and based on different vertical land motion estimates. And in the center, you see when you correct tide gauges with our data, and the last parameter shows when you correct it with the GA model, and the first part shows when the sea level reconstruction from Sönke-Dangendorf. So there can be differences. And for the altimetry community, this vertical land motion data set can be also very useful, because you have a global estimate and you can correct tide gauges for this. So you can derive the absolute sea level change at tide gauges and use this to compare that with your altimetry-based trends. Now, as I said in the beginning, we interested how vertical land motion is going to affect relative sea level change also in future. So we kind of reassessed current sea level projections and used the latest sea level projections from the AS6 assessment report. So we used the middle of the road emission scenario SSP2 and performed like a sea level budget, adding the contributions of vertical land motion and absolute sea level change, and then we wanted to understand what are the major contributions to sea level uncertainties. And here I show a map of future relative sea level changes in 2150. And below I show some time series where the green line shows the projected relative sea level. The blue shaded area shows the uncertainty contribution from absolute sea level as projected, and the orange area shows the vertical land motion uncertainty contribution. And as you can see, that can be in some regions that can be of similar magnitude. So far this was really underestimated, and these large uncertainties stem mostly from these highly nonlinear variations. Also, we know that vertical lamp motion shapes a lot of the regional variability in relative sea level changes, and we can plot the different components for different regions like Baltic Sea, Western Europe, and I showed here also two different scales, like the deviation from the global mean sea level change in 2150 and the absolute change. And we see that this regional variability is highly influenced by vertical lamp motion, and that contribution explains about 50% of the regional variation. So it's almost as large as the projected changes due to changes in ocean circulation and mass changes. Also, I show here the uncertainty contributions at these different regions, and in particular in Western South America, where we have high tectonic activity, for example, or in Japan, we have a strong dominating impact of vertical lamp motion on these uncertainties, and they are even larger than the absolute sea level change uncertainties. And overall, that contribution explains about a third of the projected uncertainties. So with this analysis, we want to put the focus on also adequately modeling these nonlinear variations and accounting for that in future projections. And we also have to account for that if we correct height gauges, for example, when they are affected by nonlinear vertical lamp motion. So that's important for validation of altimetry as well. And we will soon publish the data. You can also get in touch before it is published. And I also added some links to some nice software used for the interpolation, for example, or we also provide like a discontinuity detection software in GNSS time series. So if you find this useful, please use it or ask me if you have any questions. Thank you very much.
Is there some questions? I have one, Julius. How do you select different type gauges that you use for your study? Do you reject some type gauges, and why?
So we use only well, I think metric PSMSL type gauges, and we try to limit the manual treatment of the data, but I also applied some kind of a regional comparison of tight gauge trends, and if there are really strong outliers, I would remove them. But usually, like outlier analysis is very objective, like a check if there's really a high uncertainty in the data, or if there are some very, very irregular events, then I would reject them as well. Yeah.
No more questions? Okay. So I think we can have the next speaker, which is Fabio Mangini.
Okay, hi. My name is Fabio Mangini, and I work at the Nansen Center in Bergen. With today's presentation, I will be showing you the last project I've been working on, that is about the mass component of sea level along the coast of Norway on intraannual time scales. It is a project I've been working on together with other people, and in particular with Antonio Muraduce, Roshin Raj, and Leon Shafik, that are all researchers from the Nansen Center in Bergen, and with Leon Shafik, that is a researcher at the Department of Meteorology of Stockholm University. Actually, it's not in the list, but I should also mention Joni Johansen, that he also works at the Nansen Center, and he suggested the idea for the project. To start the presentation, I would like to say very few words about the mass component of sea level and what we mean by that. And with mass component of sea level, we refer to changes in sea level that are due to changes in ocean mass. And the idea behind that is quite simple. If water converges in one region, then sea level tends to rise, and if water diverges from that region, sea level drops. And this can be due because there is an exchange of water between ocean and land, for example, due to melting of ice sheets or glaciers, but also because there is a redistribution of water within the ocean due to the contribution of winds or pressure. And in this project in particular, we will be dealing with the contribution of winds to the mass component of sea level on intraannual timescales along the coast of Norway. And we'll be using monthly data over a period that goes from April 2002 to April 2019, so over an 18 years period. For this project, we will be using two sets of independent estimates for a mass component of sea level that we derived using a combination both of remote sensing observations and in situ observations. And the reason why we opt for two sets of independent estimates is to assess in a way the robustness of the results. And the idea, again, is relatively simple. If we find the same results using the two independent estimates, then we are more confident on our conclusions. The first set of estimate, we use for the first set of estimate, we use a combination of satellite altimetry and hydrographic stations. At each hydrographic station along the Norwegian coast, and you can see them in the map, there are 8 of them, we compute the mass component of sea level as the difference between the full sea level signal that we can calculate using a coastal altimetry dataset and the steric sea level, which is the sea level changes due to changes in density, and that we can compute using the temperature and salinity profile provided by the hydrographic station in question. When it comes to satellite altimetry, we used a satellite altimetry dataset that is reprocessed using the ESA-ESRIN tracker. We use 1 Hz, we have a 1 Hz posting rate. And we opted for this dataset because in a previous work we found a good agreement with a Norwegian set of tide gauges. For example, here is the case for the comparison between satellite altimetry and tide gauges for the trended and the seasonal signal. And we can see that correlation, I can see very well, that should be between 0.8 and 0.95, and the root mean square difference mostly between 1.5 and 3.5. And yeah, and it's using coastal altimetry can be advantageous in a way because we can reconstruct the sea level signal centered at each tide gauge location. Whereas, for example, there is never a perfect overlap in space between a tide gauge and a nearby hydrographic station. But also because it makes, in a way, the project more applicable to other regions more easily, because not all regions of the world are as well covered as the Norwegian coast. When it comes to the second estimate, we use the GRACE and GRACE follow-on data. GRACE and GRACE follow-on are two satellite gravimetry missions. GRACE has been operative between 2020 and 2017, whereas GRACE follow-on has been operative since 2018. And they have almost a full coverage of the Earth, and they provide values of the gravitational field with monthly data, basically. And this information of the gravitational field is important for us because, as I was saying before, changes in mass component of sea level means changes in ocean mass, so basically changing the gravitational field. And that's why GRACE can provide information on the mass component of sea level at the time scales we're interested in here. And before I was saying that we use two sets of estimates, and it's quite good because we can assess the robustness of a result, but also they allow us to assess the quality of the present observing system, or at least the one that we're using. And that's because both of them are issues. We saw that satellite altimetry worked pretty well. We saw that in a previous work, but when it comes to the hydrographic stations, they might it's true that the Norwegian coast is quite well covered because there are 8 of them, but it's also true that the Norwegian coast is like more than 2,000 kilometers long. So in a way, the hydrographic stations that are present might undersample the changes in temperature and salinity in the area. And for example, if you look at this one is just an example for the station that is in front of the Sonja Fjord, that is the longest fjord in Norway. And in theory, it could be strongly affected by the exchange of between the fjord and the ocean. And so temperature and salinity data provided by the station could be represented for a small area. When it comes to Grace, Grace itself has some issues, especially in coastal areas, and that's because it has a relatively poor spatial resolution of nominally of 300 kilometers. And so in the coastal areas, it doesn't distinguish well between changes in the gravitational field that are due to changes in water over the coastal ocean and over land, where you can also have variation in the amount of water due, for example, to precipitation or snow coverage. And that's why in this project, we use a data set that has been reprocessed using a Mascon approach, that the purpose is to reconstruct the mass component of sea level using basically observation over the ocean. And we use a product provided by the Goddard Space Flight Center. As I was saying, we also consider the contribution of winds. So we're interested in the contribution of winds on inter-annual time scales. So we IPAS filter all the time series with a 12-month running mean. And then we consider the local winds for, on the one end, because to assess its contribution, for example, Grace has not been used in the region, so we can see it's the contribution of winds, but also to provide a further evaluation of the estimates, physical evaluation. And that's because we know that at these time scales, local winds, in particular that blow along the continent, basically along the coast, but along the continental slope, they can affect local sea level through aquam transport by transporting water on the shelf or away from the shelf. And so we can see whether the two set of estimates that we consider make sense in respect to the winds, to the local winds. And so that's I can start showing some of the results. Here we have we consider two cases, like we consider the along slope winds blowing along the north section of the continental slope, which is the map on the left, and the Norwegian section of the continental slope, which is the map on the right. And we did a simple linear correlation between this along slope component, actually of the wind stress, and the mass component of sea level provided by Grace and by the combination of satellite altimetry and the hydrographic station. And this is the result. And the result in a way makes sense. What the colors say basically is that if you focus just on the map on the left for simplicity, if the winds blowing in the north-east direction, then you've got high mass component of sea level on the shelf and low over the open ocean, and vice versa when winds blows in the opposite direction. And this actually makes sense in terms of aquam transport. You can also see a good agreement between Grace and the combination of satellite altimetry and the hydrographic stations. If you consider the linear correlation coefficient provided by by the two set of estimates, we pick, for example, one grid point from Grace in nearby hydrographic station, and we compare the estimate from Grace for the combination of satellite altimetry and the hydrographic station. We find that the average along the Norwegian coast, the difference is less than 0.15 percentage points. And another thing that was interesting is that we can see that Grace actually is able to very well capture the presence of a continental slope and the shelf, even though it nominally is a relatively poor spatial resolution of, as I was saying before, 300 kilometers. And we see that Grace can also capture variation within the shelf. If you consider the winds over the North Sea section, this show a higher correlation in the northern part of the North Sea and the Norwegian shelf, whereas the winds that blow along the Norwegian part of the section show a higher correlation with the Norwegian shelf and the mass component of the Norwegian shelf and the Barents Sea. We didn't only consider, in a way, the covariability between the signals, but also in terms of amplitude. And in this case, we consider the average along all the Norwegian, the hydrographic stations, basically the average along the Norwegian coast. And in the upper plot, you've got the mass component of sea level average along the Norwegian coast provided by satellite altimetry and the hydrographic station, which is the blue line. and from GRACE, from the Goddard Space Flight Center Moscow solution, which is the orange one. And you see that, as expected from the previous map, you see a good agreement between the evolution of the two time series, but also in terms of amplitude, the two are comparable, with values that go from approximately -5 and 5 centimeters. And in the plot underneath, you've got the comparison with the long slope wind stress blowing along the North Sea section of the slope. And you see that GRACE, but the same would have been for the other estimate. You see a good agreement between the two time series. Together with that, we also try to consider not only the contribution of local winds, but also of remote winds. And in particular, we consider the winds blowing along the western part of the continental slope of Europe. And these winds should affect sea level locally due to Ekman transport, but in fact, there is this theory according to which sea level perturbation generated in this region of the ocean is able then to propagate further north in forms of coastally trapped waves. And therefore, we might expect that the winds in this location might be somewhat related to the mass component of sea level in this area along the Norwegian shelf. And when we compare the two, here, I consider the integrated long slope winds over this section between the two processes. And when we compare the integrated long slope winds with the mass component of sea level, from which we removed the contribution of local winds through linear regression, we find a positive linear correlation, both when we consider the combination of satellite altimetry and the hydrographic station, and when we use GRACE. And this is a correlation that go between I think 0.35 and 0.55, and significant. And so we can get to the conclusions. Overall, we found that both GRACE and the combination of satellite altimetry and the hydrographic station give comparable contribution over the Norwegian shelf, at least in inter-annual time scales. And we see that apparently they capture a physical signal in the area. And in fact, we found a similarity, especially with local winds, and to a lesser extent with remote winds in the area. That has been, and so in a way, we could quantify their contribution. And actually, I didn't show that we also use some other GRACE datasets, and in particular from JPL and the Center for Space Research, and we found very comparable results. And so the idea is that this is hopeful in a way that we can maybe use this dataset to study the mass component of sea level in other areas of the world where there are not as many in situ instruments as along the Norwegian coast. And future work, I forgot about this slide, sorry, is that there was Frank Thompson that unfortunately couldn't join today, actually at the conference because he had an issue, and that he was start thinking about using the mass component of sea level along the coast of Africa, especially in the south. You've got a broadening of the continental shelf along the coast of South Africa and I think it's called Namibia in the southern part of Africa on the western side. And so it was thinking maybe we can try to consider mass component of sea level in the area. And when it comes to also, we were thinking not to consider the contribution only at inter-annual time scale, but also longer time scale like inter-annual. And and these, these are just extra slides. Okay, thanks a lot.
We have time for questions.
I have two questions. The first one is, which is the product that you use from, from where you download GRACE data, because I use a MySCON product, and you have the actual spatial resolution is 300 kilometers. So I am surprised, but in a good way, that you have a really good result in a really fine topography.
Where I got the data, this one was from the website, I think, of the Goddard Space Flight Center, and you can download the equivalent water height from. I can show you the web page if you want. But actually, it's only part of the truth in the sense that the data set that I used is on a regular grid, 0.5 times 0.5, and this is, I don't think is still available on the website. I got it directly from Brian Loomis, that I think is the person responsible for this data set. You can find regular data on a regular grid, but I think just the ocean bottom pressure. But anyway, I can show you the website where I downloaded all the free data sets.
Okay, yeah. And the other question is, when you show the correlation map, I was wondering how you obtain that map. If you are correlating the coastal with the wind, with the map of the wind, or you are just assuming that the stated height on the hydrographic station will be the same all in the area around that?
No, I teach grid point. Sorry, you mean to create this?
Yes.
Yeah, for the grid, I consider I average the long slope wind stress along, for example, the thick black line, and I've got basically an index monthly data. And I made a linear correlation with at each grid point with the mass component of sea level from grace. And then at each hydrographic station, I did the same. I did the linear correlation between this component of its wind and the mass component at each hydrographic station individually. So yeah, I didn't assume any how do you say that? Any coherence, spatial coherence in a way. Yeah.
Okay. Thank you.
But yeah, if you want, we can chat later. If you, I'm not sure I answered the question. Sorry.
Yeah, we can talk later, and also we can talk about term using grace because
yes,
something with that.
Yeah, okay.
Other questions? No.
Okay.
Thank you, Fabio.
Thank you.
So we are just on time for the lunch break, I think. Thank you.
Can you hear me? Oh, beautiful. We all go down in the court and look up and be on the picture. Be on the picture. Okay? Before lunch. Now. Let's go.